So hello, everyone, and thank you for joining us in this really interesting open source summit today. I'm Piero. I'm from Uber AI, which is the part of the company that specifically works on artificial intelligence problems. In particular, I work on conversational AI, which is, if you're familiar with Siri, this is the kind of thing that we are working on, in particular to provide new tools for our customers and in particular for our drivers. And the project that I'm going to be talking about today is Ludwig, which is a project that we released as open source recently. It's just, I think, about a couple months ago, less than a couple months ago. And so what is Ludwig to begin with? It's a deep learning toolbox that is based on TensorFlow, so we're not reinventing the wheel, we're using pretty solid open source tools, and we're building on top of them. And what it does for you is that Ludwig allows you for building deep learning models without writing a single line of code. The basic principles around which Ludwig is built is, first of all, it's a general solution. We made it so that it's based on abstraction, which is a data type-based abstraction that I'm going to tell you a lot about in detail in the remaining of the presentation. And this abstraction actually allows for many machine learning applications to be developed with Ludwig pretty easily. And it's also pretty flexible. It allows both users that are novices in machine learning, but also users that are more experienced, both to find value. Because for unexperienced users, they have an easy way to get to a point where they have a model that actually works. But experienced users actually can modify all the parameters of their models and get all the nitty-gritty details and change every single little thing. So it provides opportunities for both types of users. It's also extensible because Ludwig contains many models, as you will see, but keeping up with the pace of research is pretty difficult. So we made it so that there are pretty simple common interfaces, and users can add their own new models to Ludwig pretty easily. Moreover, the deep learning models are pretty hard to visualize, in particular to visualize the internals and what actually is going on within the model. But Ludwig provides you with some visualizations that make it possible for you to look at what's going on, at least at the level of the accuracy metrics and in general the measures that you have for the quality of the predictions of your model, and also to look at what are the predictions compared to other models. It's really easy to use. I will show you. There's also a programmatic, even if you don't have to write a single line of code, there's also a programmatic interface that's super simple. You just have to write 2 lines of code in order to either train a model or to use it for prediction. And finally, it's open source under Apache license 2.0. So if you're interested in contributing, please reach out. There's plenty to do, and we have a lot of big plans for Ludwig to grow, even in particular with the help of the open source community. So let's start with a simple example of how it works, and then we will get more into the details later on. So let's suppose we have a data set, and this data set is structured this way. It's a table where you have one column, which is, for instance, the body of a news. And the class, which in this case is one among different types of classes. Excuse me, I'm really sorry about this. All right. The class, which is one among several different classes that this news can belong to. So what you can do with Ludwig, you can use this data set to train a model. And it's really easy. The command that you have to write is the one that you see at the top, Ludwig experiment. You specify where's the CSV file, and then you specify a model definition, which is actually the core of Ludwig, and the part that we're going to spend much time during the presentation to explain how it actually works. But at a superficial level, you can already see that there are 2 parts of the model definition. One part is the input feature, and the other part is the output features. Both are lists. It means that Ludwig can support several input features and several output features. But in this case, we only have one input feature, which is text, and one output feature, which is class. And those names are exactly the same names of the columns of the CSV file that we are providing. And the only additional thing that the user has to provide is the type of the column. For text, the type is actually text. And for class, the type is category. And depending on that, Ludwig will create a deep learning model for you that will be trained afterwards. In particular, what it's going to do at the beginning is going to split the data set in training, validation, and test. It will train on the training set until the accuracy on the validation set, the peak accuracy is reached. And after that, it's going to use the best model on the validation set to predict on the data points that are in the test set. So if you run that command, what actually happens, all right, this is like the output at the first epoch of training. As you can see, you're going to see for the output class all losses and also some metrics of accuracy, and in this case, it's at k, which is just a way to say how many correct classes do I have in the first k suggestions from the model. And then, all right. And then after a few epochs, peak accuracy is obtained. In this case, at the fourth epoch, we reach 91% accuracy on the validation set. And after a bunch of other epochs, there has not been any improvement. And so after 10 epochs, by default, Ludwig interrupts training and returns you with the best model that it has found during the training phase. And this model is used to predict on the test set. And those are some of the metrics that Ludwig outputs so that you can figure out if those predictions actually are useful for you, if they do make sense. And it also provides for each single class all sorts of metrics. So it's both generic metrics that are overall the data set and metrics that are specific for each class. And this is basically Ludwig in a nutshell. As you can see, we've trained a model. We haven't written a single line of code. But now, what I want to talk about is actually how does it work, what's going on behind the scenes, so that we have all a better understanding of what Ludwig can do for you. In particular, as many different, machine learning tools, Ludwig has this notion of training and test, which is, or training and predict, which is actually pretty natural for a machine learning model to provide. And so what happens during training is that you provide some raw data, in this case, the CSV file that we've seen before. And there's a module that performs some preprocessing, maps this raw data into tensors. While doing so, saves some mappings. So for instance, before we had all those classes are going to be mapped into integers, and this mapping is going to be saved in a JSON file. And the reason is that this mapping is going to be used afterwards when we're going to do the prediction in order to map again the data back into tensors. And so with the data that has been mapped into tensors, a model is trained, and both the weights and the upper parameters of the model are saved. At prediction time, what happens is that you have some new data, and this data is going to be mapped into tensors with the same mappings that we obtained during the training phase. The model is going to be loaded from the weights and the upper parameters that we obtained during the training phase, and this new data is going to be passed through the model. The model is going to return some predictions, and those predictions are going to be mapped back into data space using the mappings that we obtained at training time. So what we have seen before, the experiment command, is actually doing both things at the same time. First performs the training, and then performs the prediction. And what it gives out is a CSV file with the predictions labels, and also a JSON file containing the training statistics and another one with the test statistics. All these files actually can be provided to a visualization module that is going to, in the end, provide you with some graphs of the quality of your predictions. And at the end of the presentation, I'm going to show you a bunch of those graphs to give you a glimpse of what the visualization model can do for you. So under the hood, the way it works is based on three main ideas. The one is the data type abstraction that I'm going to show you. The second one is the fact that you can provide a model definition, either with a string, like as we did before, or with a YAML file, which is just a pretty readable markup language, really, really simple. And both of them are going to be treated exactly in the same way. And finally, the other piece to the magic is the fact that it uses KV-args. If you're familiar with Python, what KV-args is a way to provide a dictionary with keys and values as arguments to a function. And Ludwig uses this extensively inside his code to make it so that you can specify some parameters in your model definition file, and those parameters map one-on-one with the arguments of the functions inside the code. And so if you had a new piece of code, all the parameters of that new piece of code are going to be exposed in the YAML file. So let's talk first about the data type abstraction. Going back to our example, this is the part that is actually the model definition. But this is what we provided. This overrides some defaults and merges the dictionaries of the defaults with what we are providing. So what happens is that the real model definition is actually all this stuff, which is divided in 5 different sections. The red one is the input features, and the yellow one is the output features. We've already seen an example of those. The orange one is the combiner, and the combiner is useful when you have multiple input features and you want to combine information from all the input features. And then you have the green part, which is a bunch of training parameters, and the blue one, which is a bunch of preprocessing parameters. And we're going to take a look at all of them in detail. In particular, the structure with encoders, combiners, and decoders is really flexible, and it's actually the main contribution of Ludwig. The reason why it's flexible is because it provides you with a way of encoding information for different types of data. For instance, for text features, for numerical features, for categorical features, for sets, for images, for time series, for sequences, and does the same thing also for the outputs. So each single data type has a way to map from a representation that is provided by the combiner into an output through a different decoder. And at each single application that you build with Ludwig is not going to use all the input data types and all the output data types, but the combination of them provides you with several different applications. So for instance, the example that we have seen before uses a text input feature and a categorical output feature in order to obtain a text classifier. But if you have, instead of text, you have an image as input and text as output, then what you're doing is, for instance, an image captioning system. Or if you have some categorical, numerical, and binary features as input, and you have a numerical feature as output, what you obtain is a pretty classical regression model. And so as you can see, mixing and matching the different types of inputs and outputs, you can obtain many, many different applications. And I will show you some of the ones that we're actually using inside Uber later on during the presentation. An additional advantage of this architecture is that each single input can have different encoders, and each single output type can have different decoders, so that the user has a wide range of options to select from when building their model. So for instance, for text, we have, at the moment, the first 5 encoders. The transformer is going to come in the next release of Ludwig, probably next week, most likely. And so the advantage here is that the input and output, the input is basically raw text, and the output is a vector. And everything that is happening in the middle is actually the core of the model. For instance, in the stacked CNN, there's several layers of convolutional neural networks, while in the parallel CNN, you have several layers of convolutional neural networks running in parallel, one to each other. In the stacked parallel CNN is a combination of the two. You have parallel CNNs and you have a stack of parallel CNNs. In the RNN case, you have recurrent neural networks with, you can specify also the cell if you want to have an LSTM or a GRU. you can define all these other parameters. The CNN RNN is a combination of convolutional neural networks and recurrent neural networks. And finally, the transformer uses an attention mechanism to encode the text. And moreover, an additional, one thing that I actually added recently is I'm going to tell you about that later, actually. Yeah, no worries about that. So, and in order to specify one of those encoders, all you have to do is to provide those first 4 keywords. In particular, name, which is the column in your CSV file that contains the data. Type, in this case, is text. Encoder, which is the name of the encoder you're going to use, in this case, parallel CNN, and the level, if you want to use words as basic elements, or if you want to use characters as basic elements. All the remaining parameters are hidden from the user. You can specify them if you want to have additional control over your model. So for instance, you can change how many filters the convolutional neural network is going to have, or what's the width of the windows that the convolutional neural network is going to look at, or how many, what's the dimension of the fully connected layers that come after the convolutional neural network. You have full control on all those parameters. But by default, if you don't specify them, these are the default parameters that you're going to get. And the really nice thing is that actually, if you want to have a different, actually, those parameters, as I was saying, map directly into the code. So this is like the init function of the parallel CNN object that implements the parallel CNN. And there's a one-on-one mapping between the parameters that are there in the configuration file that I was showing you before, and the parameters that are the input parameters of this, the input arguments of this function in the code. And if you want to use another model, like for instance the stacked CNN, all you have to do is actually just change the encoder to stacked CNN instead of parallel CNN, and then you have a completely new model at your disposal. Obviously, this model has different hyperparameters and that you can tune, so if you want, you can play around with those parameters too. But the advantage is that you also have the stacked parallel CNN, the RNN, and the CNN RNN. All of them are really easy to swap in and out. You just have to change one string, which is the encoder string in this case. And for instance, in this case, with the CNN RNN, you have also the parameters of the RNN, like if it is bidirectional, if it has what is the cell type that you can use, what is the state size of the RNN. So each single encoder has different parameters, but swapping between them is really, really easy. So this is something that I added in the latest version of Ludwig, version 0.1.1. Now there's a bunch of languages that are covered for doing preprocessing. In particular, we have English, Italian, Spanish, German, French, Portuguese, Dutch, Greek, and multi-language. Multi-language is going to be used when you don't really know what's the language of the text that you're going to have to encode. For instance, when you have user-generated data, that's most likely the case. And so Ludwig takes care of splitting and tokenizing and doing preprocessing on text for you in all those languages. The advantage of having an architecture like this is that then it's really easy to reuse code. In this case, I basically reused 100% of the code that I'm using for the text features, also for sequence and time series. And as you can see, the encoders are exactly the same, and they're available. You write them once, and those are available for all the sequential type of features. And a similar architecture is also provided for image features. The image part is not as developed as the text part, but the two encoders that we are providing are a stacked CNN, which is similar to VGG, if you're familiar with that architecture, and which is pretty performant and well-suited for relatively small images and relatively small data sets. And we also provide ResNet, which is better suited for bigger data sets and bigger images. All the other input data types are encoded with just one encoder. because they are much more simple, so they don't require all the full spectrum of different encoders. For instance, category features are encoded either as a one-hot vector or with a dense embedding. You can choose among them. And numerical and binary features are actually encoded in a really simple way. Binary features are just mapped into floats, and they are directly used, while numerical features, you can specify to use one neuron for actually for scaling the values, if you want. And finally, sets and bags features are also made available to you. The way they work is each single element in the set that you are providing is going to be mapped into an embedding. And all the embeddings of all the elements in the set are going to be aggregated by an aggregation function, and the output is going to be passed through some fully connected layers. For the bag works exactly the same. The only difference is that because you have the frequency of the items in the bag, the aggregation function takes that into consideration, providing you with a weighted average. So now we have all these encoders for all these different data types. And what if we have more than one feature, one input feature, if we have several of them? Ludwig provides you with this mechanism of combiners that allow you to combine information from all your inputs. There's several of them. The one that I'm showing here, the concat combiner, is the most simple of them. And what it does is it takes the outputs of all the input features, concatenates them, and then passes them through some fully connected layers. And how many layers, how big are those layers? You can specify that through the parameters of this function. But by default, you don't have to specify anything. This happens for you automatically. And now we're at the decoding side. So after we combine the information of all the different inputs into one single representation, now from that representation, we want to provide the predictions. And if the output data type of your feature is category, what is going to happen is basically Ludwig is going to provide you with a multi-class classification setting. And you have a bunch of parameters here too. You can change the loss. You can change some additional values for the loss, like for instance, if you want to use robust lambda, or if you want to penalize overconfident predictions. There's a bunch of parameters that are at your disposal here and that you can change. And something similar happens also for numerical features. In this case, the loss that is going to be used by default is mean squared error, but you also can use mean absolute error, and also R2, if I remember correctly. And similarly, what happens for binary features is that you have binary cross entropy as loss, and you can specify all the parameters of this loss. In particular, the last parameter there, which is the threshold, so you can decide where to put the threshold of your binary classification. The most interesting of the different outputs is actually this sequence decoder, because in this case, we have two different types of decoders, while for all the other outputs so far, we had only one output decoder. So here you can have either a generator or a tagger decoder. The difference is that the generator decoder actually generates a sequence token by token, providing the token that is generated at a specific moment in time as the input to the next moment in time, and keeping on going until a specific token which highlights, which actually is the end of sequence token, is produced by the model. While the tagger is a different type of decoder, which assumes that you have a sequence as input and provides you with a mechanism for classifying each single element of the input with a class. And we're going to see an example later of both of them, an example of a generator and an example of a tagger. Finally, the set feature decoding. Basically, what it will build for you, it will build a multi-label classification where each single object that you provide as input can be actually tagged with several different classes. And here, the loss is going to be sigmoid cross entropy, because each of the different elements of the set that you are providing as supervision can be predicted independently of the others. I added this neat little feature that is actually not super common, and I haven't seen this thing implemented in other in other machine learning libraries, to be honest. What this thing is in some cases, when you have several different outputs, the output that you provide for one of them is actually useful for informing the model that is going to produce the output for the other one. Let me give you an example. I was working on a customer support model last year, and there is, in that model, there are two predictions that we want to make. One prediction is to figure out what is the type of the customer support ticket that we are receiving, and the other output is which among several different answer templates we want to use for answering this ticket. In this case, obviously, if you know what is the type of the ticket, that's an important information to decide which answer you're going to give to the ticket. And so in that case, what you can do with Ludwig, you can specify dependencies between different outputs so that you just specify a list with all the other outputs that a specific output is dependent on, and Ludwig builds a directed acyclic graph for you that takes care of providing the output of one as input to the other ones. Then you have the last two pieces in the model definition, the training parameters, and here we spend a lot of time creating a training loop that has many, many options for you. And you have actually several different things that you can change here. You can change the batch size, you can change the number of epochs, you can change the learning rate, all these sort of things. Plus there are some more, let's say, complicated ones, like for instance, the logic that manages the plateau of the performance. For instance, if you reach a specific performance on the validation set and then you cannot improve over that performance, you can specify how many epochs you have to wait before interrupting the training, and so on and so on. This is just a small selection of the parameters that you have. So this shows that it's actually a really, really flexible training loop that you can work with. And finally, the last piece of the model definition is the preprocessing parameters. Here you can specify some preprocessing parameters that are generic. For instance, when you want to split the data, how you want to split it. In this case, by default, it's split in 70% training, 10% validation, and 20% test. But you can change that parameter and split the way you want. And then there are some parameters that are specific for each single data type. For instance, for text, for categories, and so on and so on. And these parameters for preprocessing are going to be applied to all the text features. For instance, how long is, what is the maximum length of the text that is going to be provided by the user? Or how many words are going to be there in my vocabulary? All these hyperparameters, you can change them. But these parameters work at the level of the data type. So if you have two different text features, for instance, one which is, I don't know, the title of a news, and the other one which is the body of the news, then you can also specify these preprocessing parameters specifically for each single feature, because, for instance, for the title, you want the maximum length to be probably, I don't know, 20 words, while for the body, you want the maximum length to be probably 500 words or something like that. So you also have this flexibility. All right, so now that we have an overall understanding of how a model definition in Ludwig works, let me show you some example of model definitions that can be used for building models that are pretty close to the ones that we're actually using in production at Uber at the moment. So this is going back to the first example that I showed you, the text classifier. This is the structure on the bottom right of the model, and all you have to specify to obtain this text classifier, given that data, is that model that you see there by specifying one input feature of type text and one output feature of type category. But if you want an image classification model, for instance, as you can see, the difference is super small. The only thing that you have to change is the type, and you have to specify image instead of text. And obviously, you have a different set of encoders that are available for you for images, so you want to specify which encoders to use, in this case, the stacked CNN. What if you want to have a model that trains from exchanges between two users? So you want to train a model that is kind of a chit-chat dialogue system. If you have data structured this way, where you have one column with what is uttered by user 1 and one column with what is uttered by user 2, you can just specify one input feature, which is of type text, and in this case is encoded with an RNN using an LSTM cell, and an output feature that in this case is also text or sequence. In this case is exactly the same, doesn't really change. In this case, we are going to use the decoder, which is the generator, because the two different sequences can have different lengths. And you can also specify attention, which is an additional mechanism that allows for models to perform better at generating sequences. Another example is this expected time of delivery model. This is like a small subset of a model that is actually being used in production for predicting the delivery time of orders in Uber Eats. And the way it works is you specify a restaurant, which is encoded as a category. You specify the order, which is a set or a bag, if you have repeated elements, of items that have been ordered by the user, and also what time of the day this order was performed, in particular the hour and the minute. And what you're going to predict is the ETD, which is the number of minutes that it's going to take to deliver this order. And you can see from the architecture there that you basically specify all the different input features. There's a combiner by default, the concatenation combiner, and then the prediction of the ETD is going to be obtained from the output of the combiner. And this is actually an example of a tagger, what I was telling you before. In this case, you have sequence utterances with each single word mapped into a tag. For instance, in this case, we want to figure out what is the type of each single word, what type of entity is it. And John Smith is mapped to P, which means person, O means I don't care, C means city, and New York is aligned with C and C, and D is for the date. So what happens here is that if you specify that your output is a sequence, and you specify that the decoder is tag, if you are sure that all your input sequences in the utterance column and the tag sequences in the tag column are one-on-one aligned, Ludwig is capable of training a model that will provide all the tags for your input sequence. There are some additional goodies, in particular the programmatic API that are provided for you so that you don't have to use code, but if you want to, you can. First of all, to install Ludwig is really easy. You just have to do pip install Ludwig, and it's going to be installed right away. And in order to use it programmatically, you just need basically 2 lines of code. The first line of code is the importing the Ludwig model from Ludwig, and then you're going to create a Ludwig model, initializing that class with a model definition. And the model definition here is a dictionary that contains exactly the same information that is in the YAML file that we've seen so far. Once you build a model, you can call the train function on a set of data, and at the end of that call, you're going to obtain a model which has been trained. And if you train the model, then you can use the model for obtaining predictions with model.predict on a new set of data, and that is going to return the predictions from that new set of data. Or if you already trained a model beforehand and you want to load a pre-trained model, you just have to specify ludwig model.load and the path of the model on disk. Other additional goodies is that Ludwig is pretty well integrated with a bunch of other tools that Uber provide both externally and internally. In particular, works really well with Horovod, which is a library that allows you to train on multiple GPUs and on multiple machines with multiple GPUs without much effort. And so if you want to train a Ludwig model on multiple GPUs and multiple machines using Horovod, all you have to do is you have to specify the -- use Horovod flag when you're training the model, and that it's all taken care for you. And it also integrates with other internal tools that we have at Uber, in particular for doing serving with what we call PyML, and for hyperparameter optimization with auto-tune. And I will show you an example of the hyperparameter optimization. So, as we have seen, the overall architecture of using this encoder, combiners, and decoders is really flexible and allows also for many different options for you to try. And it also allows for plugging in and out new pieces of code and new models, which is great for experimentation, because in the end, all you have to do once you put the code into the Ludwig format is just calling the name of that new encoder or decoder that you provided, and it's all taken care for you, and you can run a new experiment just changing one string in your YAML file. This quality actually helps a lot when you have to do hyperparameter optimization, because for instance, let's assume that you specified your Ludwig model, but you want to figure out what are the optimal parameters for your Ludwig model. Well, this is an example of how we do it internally. This thing is not released as open source because it's pretty tied to our own infrastructure, so it doesn't make much sense to release it as open source, but something similar can be used also by people externally. The way it works is you have on your left hand, you can see like there's a default model definition that you provide, which is the same thing that we've seen so far. And on the right-hand side, you see that the two parameters that I want to optimize are the dropout, the training dropout parameter, and the embedding size of flow node, which is one of the input features. I specify some ranges, and depending on the strategy for optimization that I want to have, a bunch of samples from those ranges are going to be obtained. Those are going to be run in parallel on several machines, and the results are going to be saved into one single location for you to analyze. And because you can have many different results from that, we provided also some visualizations so that you can compare different models easily. When you train a model, what actually happens is that a CSV file with the predictions is saved, but also a JSON file with the training statistics and a JSON file with the test statistics are going to be saved as well. And from these files, you can just call some really easy visualization commands from the Ludwig command line. And what you obtain is a bunch of visualizations. This is just a selection of some of them. There's, I think, more than 12 of them. And those are really helpful for you to understand what's going on with the model. In particular, the first one provides you with a comparison of different models on different metrics. The second one is a calibration plot to see how accurate are the probabilities that you are predicting. The third one is a graph that shows the coverage against the accuracy obtained by swiping a threshold on the probability that the model provides. The fourth one is actually a 2D projection of the same 3D space. The fifth one is a comparison between two models. The green part is where the two models provide the same prediction and the prediction is correct. The yellow part is where one model provides the correct prediction and the other one is wrong, and vice versa. And the orange one is where the models are wrong, either providing the same prediction, the same wrong prediction, or different predictions, different wrong predictions. And the last one, the last graph, is actually a graph where you can see the F1 score for each class in your category class that plotted against the frequency in the data set, which basically shows that you're probably performing well on more frequent classes. So as I told you before, Ludwig has been released about 2 months ago. And since then, we've already released an updated version which solves some of the bugs that we discovered with the help of the community and also introduces some new features. But we have many more features that we want to introduce. In particular, we want to have also speech as a data type, also videos as data types, or point clouds as data types, because those are going to be really helpful for many, many more applications to be developed with Ludwig. And we also want to add more encoders. In particular, For text, these Elmo, BERT, and GPT are pretty widely used at the moment, and they are pretty effective, so we want to add them too. But actually, the main weakness at the moment of Ludwig is the fact that the only way you have to provide data is either with a CSV or with a pandas data frame. And that doesn't scale with really, really big data. So what we're going to do is we're going to integrate with Petastorm, which is another open source library that Uber released, which allows you to provide data both as a CSV or with Amazon S3 kind of format, or even directly from HDFS and from Hive. So basically, this is going to solve the scalability issues that come with the fact that Ludwig at the moment only supports CSV. So this feature is going to probably come in the next major release of Ludwig. So finally, if you want, you can take a look at the documentation. I spent a lot of time writing the documentation, so I think it's pretty extensive, and you will probably going to find everything that you need there. It's ludwig.ai, really easy to remember also. There's also the repository with the code, and there's also a blog post that we published about Ludwig, and soon enough there's going to be also a scientific paper that describes at the deeper level all the innovations that we added into Ludwig. And that wraps it up. Thank you for your attention.